differential equations, and specifically, we're going to start with a particular differential equation. So a differential equation it's an equation that involves a function and some of its derivatives. So, for example, if you had an equation like dy dt plus y equals 5, or d squared y dx squared plus dy dx plus y equals 7 or something, okay? So these are, they involve both unknown function and its derivatives, okay, in some combination of forms. Okay, now you could have other really easy ones. For example, something like that, dy dx equals 7. That's a differential equation. It's just a really simple one. And there are lots and lots and lots of different kinds of these things that we classify according to sort of their structure. So, for example, the first one here, dy dt plus y equals 5, we call linear. That maybe isn't a shock looking at it. The other one over there is what we call second order because it involves a second derivative. And then the other one that I drew here, or dy dx equals 7, well, it's just too easy to have a name. So we classify these things based on their structure and therefore what different techniques you can use to solve them, okay? And there are lots and lots and lots of different kinds of these things and lots of different techniques for solving them. So much so that there are entire courses here called differential equations, right? That is one of the MAT111. You spend all semester doing these things. Okay, so the question we want to answer is, well, how can we solve at least some of them? And also, what does it mean to be a solution to one? So why don't we just start with this really simple example, dy dx equals 7, okay? Any guesses as to how we would solve that? There's a couple ways we could think about it. Y, okay? Yeah, integrate both sides, right? So if dy dx equals 7, that means that the derivative of some mystery function is 7, and so what would that function be? 7x plus some constant, right? Okay, so we think our solution well, let me write it this way. Our y equals 7x plus some constant, okay? And then how would we verify that in fact that's correct? Yeah, if we plug everything, if we plug y and dy dx and everything back into the original equation, well, dy dx would be 7 plus 0, which is 7, and that matches the original differential equation, so check. Okay, so it solves it. Okay, now another way we could have sort of seen this to solve it would be if I think about multiplying, sort of pretending for the moment that dy dx is a fraction and cross-multiplying, okay, then this is why we call them differential equations, because a thing, a dx or a dy by itself is called a differential. And this is an equation involving differentials, okay? Well, if this is true, then this is true, okay? And so what would the integral of dy be? Y. And what's the integral of 7 dx? 7x. Okay, now we've got to put a plus c somewhere. We could either put it on the left or we could put it on the right. We don't have to put it in both places, right? Because if you've got a constant on one side and a constant on the other, you could just move one of them and then have a new constant on the other side. So we'll put it, say, on this side, and that's what we get. Okay, so two ways we could have sort of thought about solving this guy. All right, does that make sense? Okay, so we're going to look at a particular kind of differential equation that, am I good to go to the next sheet here? Yeah, or the next page, sorry. Let's look at a differential equation of this form. Okay, and here k is a constant. Okay, so the dy dt is going to be equal to some constant k times the actual variable y itself. Okay, and the question is, what do the solutions to this thing look like? How do we solve it? What does the constant k do? Right, so if k is positive versus negative, what does that tell us? Okay. In particular, let's say that y is positive and k is negative. Okay, well then the right-hand side, k times y, would be a negative quantity. And if dy dt is a negative quantity, what does that say about y? That function is decreasing somehow. Okay, and similarly, if k were positive, then we would know dy dt is positive. Okay, so we can kind of think about, well, what's the trajectory maybe going to look like just based on what this constant is. Okay, now in this case, let's actually just, for the moment, just pretend that k is 1 so that it's not there, right? Okay, so dy dt is y. We're looking for a function whose derivative is itself. Do we know any such functions? E to the x is one such function, or e to the t in this case, but whatever. There is a second one. What is it? It's not particularly interesting. 0, right, is the other one. Okay, so, right. All right, so we guess solutions are either y equals 0 or y equals e to the x. Or e to the t, sorry, because I used t here. Okay, so what does that mean, right? If e to the t, I mean, y equals 0 is not interesting, right? It is a solution, but it's a rather uninteresting one. But e to the t, that is interesting. What could we use this differential equation to describe, like natural world descriptions? What grows exponentially? What? Yes, they do. Rabbits, Irish Catholic populations. You said it, not me. Bacteria in a cell culture. Okay. Let's see, what else? Initially, virus spread. No reason that we need to talk about that. There's been nothing going on in the world for the last year and a half that involves exponential growth. Although disease modeling is a little more complicated. Not that much more complicated, but yeah. So plenty of systems in the world, right, can be described with exponential growth. Now, we cheated and said k equals 1, right, just to get our feet wet. But let's put the k back in and see what that does to it. Now, if we had come at this from a different angle, okay, how could we solve this? Like, what did we do with the easy example last time? I pretended that dy dt was a fraction, and I sort of cross-multiplied, right? So could I get everything that involves either y or dy on one side, and everything that involves t or any constants on the other? Yeah? Okay, so I could do that by writing dy equals over y equals k times dt. Okay, is that good? All right, so now what would be a good move? What did we do last time at this step? Right, I integrated both sides. If they're equal, then their antiderivative should be equal up to a plus c, right? Okay, so let's integrate both sides. So we have the integral of dy over y equals the integral of k times dt. So this is one benefit, by the way, of us having done integration before we came back to do some of these applications, because normally at this point of a calculus class, you wouldn't have heard of an integral, right? And so, but we do have that tool in our toolbox. So the right-hand side, what's the integral of k times dt? Remember, k is a constant. Almost. T plus c, but what about the k? Kt plus c, right? Because this is like asking what's the integral of 7, right? 7t plus c. All right, so that side's easy. What about the left-hand side? What's the antiderivative of dy over y? Some of you might lose a standard, right? That's what I had to have. I had to have, like in soccer, like penalty cards, right? And if you can't answer a question that you should have been able to answer, then I give you a penalty card. And yes? Huh? Yeah, natural log of y. Now, strictly speaking, it should be absolute value. Okay, but if we assume that y is bigger than or equal to 0, then we can ignore that because absolute value of a positive quantity is positive. Okay, so there's no need to worry about it. And because this is a differential equation that, like, yes, the negative solutions are valid, but they're not going to be helpful for, like, the mathematical modeling we want to do. So we'll just throw those out for convenience at the moment. Okay, so now I have here an equation, but there's no more calculus involved, right? Everything's purely algebraic at this point. And what am I trying to do here? The whole goal is to find y, right? All right, so how do I find y from this equation? How would I solve for it? Yeah. That's a yellow card answer. Yeah, e to both sides. Okay, so e to the natural log of y would be e to the kt plus the constant. And what's e to the natural log of y? Just y. Okay, and then I'm going to rewrite this as e to the c times e to the kt, right? And I can do that because that's how the rules of exponents work. Normally, we're doing that to put, like normally we go from the bottom step to the one above it, right? Putting two exponents together as one, but that certainly works in reverse, so got that. Okay, now, if c is a constant, what is e to a constant? Well, to the first.
Good morning, sir.
Good morning. Thanks for making a guest appearance.
I'm very sorry.
Yeah, well. You know, it doesn't work that way.
Yeah.
Did you run into any of your other compatriots out there where they're like tyrannosauruses that were snatching up students on their way to class, or rabid pterodactyls flying around? Huh?
It was the pterodactyl.
Okay. Kids these days. All right, so if C is a constant and E is a constant, what's a constant raised to a constant? Some other constant, right? It's just a number of some sort. So what I'm going to do is I'm going to replace the constant e to the c with the letter a. It's just a constant, right? Okay, so this gives us the general form of the solution. Okay, now, how could we check whether or not our solution is correct? Yeah, we could derive this. So let's check. So, okay, so we think this is our solution. Let's check it. What's the derivative of y here? What's the derivative of a constant times e to the kt? The constant times e to the kt times k because of the chain rule. Okay? All right, our differential equation was, let me rotate this so you can see a little better, Suni. I mean, you're the one who picked that chair, and there's no other ones available that you could have chosen, right? The original differential equation we had was dy dt equals k times y. Okay, so what's the stuff in the brackets? That's what we thought y was. And so this matches this. Check. It does solve the differential equation. Okay? All right, good. So, by the way, ODE stands for ordinary differential equation. All of the examples that we've looked at are called ordinary. There is also a category called partial differential equation, which involves things called partial derivatives that you'll learn about if you take Math 112. Okay, which I don't think is going to, huh? It does, right? What do you mean? To come today?
No. Coming every single day here is a blessing.
Uh-huh. Well, then what mistake did you make?
I don't want to talk about it.
Oh. Okay, then.
We can talk about it at a different time.
Okay. He pleads the fifth?
Yeah.
I have only actually done that once in my life. Did I tell you guys about this? Did I tell you, or did I tell all of you? When I was in 5th grade, and I had this like blood feud with the librarian. Yeah, and I was talking dirty, talking smack about her to somebody else, and she's like, "What did you say?" And it's like, I invoked my Fifth Amendment rights against self-incrimination, which only made her even more angry, and she dragged me to the principal's office. It was a good time. All right, so, right. Now, this differential equation, right, if k is negative, it describes decay, right, because e to the minus something t is going to decrease over time. And if it's k is positive, we're going to get exponential growth. Okay, so exponential growth, what did we talk about? Well, we had what things grow exponentially? Bacteria, virus transmission, at least initially, rabbit population, right? Assuming that there's infinite food and infinite space, right? Eventually they hit a wall, but, or as Mr. Burns said, you know, the population of Irish Catholics, right? That's assuming, though, that you have unlimited potatoes, okay? Right, and no potato virus. So, okay. If, however, k is negative, this is going to describe exponential decay. What natural systems follow that behavior instead? Yeah, radioactive stuff. Okay. That's probably the best example, right? So where do we use this sort of scientifically? Well, isotopes of, what's a good example? Well, okay, either like that kind of nuclear stuff, or carbon-14, which we can use for dating wood, or artifacts made out of wood or similar material, you know, basically formerly living things, right? Because what's true about carbon-14 versus carbon-12 in the atmosphere? Okay, what's carbon-14 versus carbon-12? Two extra neutrons. Neutrons. You add protons, it's a different chemical. You add electrons, you've just ionized it. By the way, how do you tell a chemist from a plumber? You ask them to pronounce this word. Then you're a plumber. All right, unionized or unionized. Well, then you know that they're a chemist. Yeah, but, okay. So, right, so exponential decay is going to be nuclear type stuff. All right, so carbon-12 is the vast majority of carbon, right? It's got how many watts and watts? How many protons, how many neutrons? Huh? Yeah, okay, so 12 protons, 12 neutrons, 12 electrons if it's in a, you know, valence, a neutral state. Okay, and most of carbon that you run into in the natural world is of that isotope, that form, okay? However, there's a small amount of it that has 14 neutrons instead of 12, right? Okay, so it's a different isotope, has different nuclear properties, and carbon-14 is radioactive, meaning that it decays over time, right? And the way that radioactive stuff decays is actually described by this differential equation. Okay, so if I have a kilogram of, let's say, pure carbon-14, right, and I just sit it on the desk, then what's going to happen if I wait 5,000 years? I mean, other than being dead. Yeah, half of it's going to be gone. Now, when we say gone, I don't necessarily mean that there's going to be less than a kilogram sitting on the desk. There might be, right? But only half of it will still be carbon-14. The other half of that material will be, I don't think it'd be carbon-12. It'd be, I don't remember the decay chain for carbon-14. Let's look it up, shall we? Oh, and it's only 6 protons, right? Because 12 is yeah. Yeah. Okay, what now? Go ahead.
Why do things just decay at half every 5,000 years?
Well, okay, the 5,000 years depends on what the chemical is, okay? So the, you know, plutonium, depending on which isotope you're talking, or let's say uranium, right, you're talking hundreds of millions or billions of years of a half-life, okay? Why? Go ask Dr. Brown. And this time literally, because like he's a nuclear physicist, right? That's like what he studies. Okay, so yeah, all right, so what's the decay chain for carbon-14? It decays into nitrogen-14 through beta decay. Okay, so probably what would happen in the case of that is because what's nitrogen going to come as in natural world? Usually as a gas, okay? So probably we would expect there to only be half a kilogram of stuff sitting on the table because the rest of it has been bubbled off as a gas. Okay, so the ratio of carbon-12 to carbon-14 before we started setting off nuclear weapons was essentially a constant, okay, because carbon-14 is produced by cosmic rays interacting with the atmosphere, and that's a relatively constant thing over the, geological lifetime of the Earth, okay, and then of course nuclear testing has screwed this up. Okay, so if you know, for example, that 1%, that the ratio of carbon-12 to carbon-14 is a particular number, and that particular number is essentially constant, right? Carbon-12 is not radioactive. So if you, dig up a tool from some, caveman site, and you can look at what the ratio is in what's remaining, and then use that to backdate it, right? So this is how we date, anthropological type things. Now, because the half-life is like on the order of 5,000 years for carbon-14, this works great for studying sort of early mankind, but it's not going to work if we want to study dinosaurs, right? Because it's just way too long of a time scale has elapsed. Yeah, exactly, right? Because at that point, there's basically no carbon-14 left. Okay, and so I guess the other thing is, so how is it that the ratio of carbon-14 ends up being that same constant in living things, particularly plant matter? Right, so the trees that are outside, what are they doing? Yeah, they're taking in carbon dioxide and photosynthesizing, and what is happening to that carbon? It makes sugars, and then also, therefore, the structure of the tree, the wood, okay, and is not released back into the atmosphere. And that process they're doing constantly, okay? So the carbon-14, the ratio of carbon-12 to carbon-14 in a living thing is going to reflect whatever the atmospheric conditions are, roughly, right? And for animals, well, we eat things that are, we either eat plants directly or eat things that ate plants, right? And so our bodies are going to have that same ratio, right? So if we dig up like a bone or something, we might be able to date it. Okay, so that's the idea of radioactive decay, right? So if we go back to our differential equation, right? The question then is, how fast does this go? Well, we just said that it depends on what material you're talking about, right? Carbon-14 has a half-life of 5,000 something years, okay? What about uranium-235? It's like a couple hundred million, okay? And U-238 is like billion something. Okay, we'd have to look up the exact number, but it's really, really big. Okay, this, by the way, is sort of interesting, okay, because unlike carbon-12 and 14, right, there's plenty of carbon on Earth, and a lot of it's in the atmosphere. In fact, maybe a little bit too much right now, but, and so it gets, huh? Well, okay, yeah. That's not how it works, but whatever. Okay, so there is a fixed amount of carbon on the planet, though, right? And a lot of it's in the ground in the form of oil, right? And a lot of it's in the atmosphere. And the stuff that's in the atmosphere is going to get bombarded by cosmic rays. Some of it's turned into carbon-14. And so, like, the amount of carbon-14 is being continually regenerated by atmospheric cosmic ray interaction. Where did all the uranium on the planet come from? Okay. Huh? No. Aliens, yeah. Where is uranium produced in the universe? Nope. Stars, in particular supernova. Yeah, when stars explode, basically anything that's heavier than hydrogen is formed, which is basically almost everything, is formed in a star, right? Helium comes into existence through nuclear fusion. Lithium and beryllium sometimes too, depending on the type of star. But eventually, certain stars give up the ghost. If you want to learn all about this, take Dr. Brown's astronomy class. They start to collapse in on themselves and then explode. And that is such a high energy event that it generates basically anything heavier than like oxygen or so. Only comes from supernova. So the fact that we have uranium on this planet in pretty good quantity, I would say, right, is because of past stars that have exploded and died and spread out their stuff all over, and then that, formed gases and accretion disks, and the solar system formed, and so on, right? So if the sun were one of the earliest stars in the universe's lifespan, and planets formed, well, there wouldn't have been any uranium yet because none of the stars would have exploded. Okay? So what that means, though, is that the amount of uranium that was in the Earth when the Earth was formed, roughly 4.5 billion years ago, was a fixed number. Right? There's no new uranium showing up unless we start going and mining other, like the moon or something, like serious mining. Okay, so what happens to that uranium over time? It decays. Now, like I said, the half-life of U-238 is on the order of 1 billion something years. Okay, so that's extremely slow. The order for U-235 is like I said, 100 million-ish years. We can look up the exact numbers. So what that means is that the ratio of U-235 to 238 today is much, much lower than it was, several billion years ago. Okay, now, why do we care about U-235 versus 238? What are they useful for? Okay, but which one do you need if you want to make a bomb or a nuclear reactor? You need 235. Oh, that's really annoying because that's the rare one. Okay, so this is why producing a nuclear weapon, the hardest part is getting a hold of the nuclear material, not actually assembling the bomb. Yeah, well, what enrichment is doing is basically you're digging up crap tons of natural uranium ore and processing it to try and separate out the 235 and 238 so that you can enrich and have a pile of uranium that's at 20-something% ratio as opposed to 0.2% ratio or whatever, right? Because for a nuclear weapon, you need it like 30, 40, like the higher the better, obviously. But for a uranium-based nuclear weapon, it needs to be quite significantly enriched. For a nuclear reactor, you want it like between 3 and 5% usually. Okay, but it comes at like 0.01 or whatever percent, right? So it takes a significant amount of work to separate out the 238, which is called depleted. So uranium that has less U-235 than it should is called depleted. And that does get used for things, just not nuclear reactors. Okay, and 235 is the good stuff, but it's the rare stuff. Okay. Now, interestingly enough, if you go backwards several hundred million years, right, and you follow the half-life backwards, there was a point in time when the ratio of natural uranium was roughly 3 to 5%. Okay, and there is one known instance of this happening in the world in Africa, where there was a natural nuclear reactor in the ground, and because the bedrock and the water table was just right, that so you can't sustain a nuclear reactor by just having a lump of U-235 on a table, right? The problem is that the neutrons coming off of it are going too fast, and so they're going too fast and they don't split another uranium atom. They just whiz by. So you have to slow them down. And what's a good way to slow them down? Water, okay? Water is a good moderator. It slows them down enough that they can then split other uranium atoms, and that sustains a energetic reaction, right? Okay, so the water table and the bedrock and stuff was such that natural uranium deposits, water would seep down, it would moderate things, and a self-sustaining reaction would occur. Now, a nuclear reaction is going to do what? Yeah, it generates a lot of heat, so what's going to happen to that water? It's going to boil off, okay, and then the reaction stops because there's no longer that moderator, and the water is boiling off in steam in the ground, right? And it's going to go up, and it's going to cool, and then it's going to settle back down again, and then the reaction's going to get going, and then eventually it's all going to boil back off. And this went on for hundreds of millions of years in the ground. Huh? Gabon. So this got discovered because I think it was the French, mining uranium, and they do an analysis on it, and they realize that the uranium deposits are way short of how much 235 that they should have. And there's only two explanations for that. Natural nuclear reactor in the ground, or somebody else has mined this and there's a clandestine nuclear program going on, right? One of them is really interesting. The other one's not so great, right? And so it turned out it was the natural one, which is, I guess, good, right? All right, so, but when we talk about radioactive stuff, what are we talking about when we describe the rate at which it decays? What's the magic number? The half-life. Okay, so how long in time does it take for half of it to decay? And so what I want to do is for us to look at how does the number k here relate to the half-life. It's not actually the half-life, but it relates to it. Okay, does that make sense? Okay, so the half-life we use the symbol lambda usually for it. Okay, so the Greek letter. And has anybody played Half-Life, the video game? Yeah? Well, now you know the symbol, right? Okay, so half-life is how long it takes for half the stuff to decay. All right, so at time lambda, oh, the other thing, when t equals 0, how much stuff is there? All of it, but it's A. That constant out front is the initial amount of material. Okay, and so if we wait around, oh, sorry, I messed this up. It should be k times lambda. Right, because lambda is a time amount, not a rate amount. Okay, so this equation describes what half-life means. Well, what are two things that you should immediately notice? What happens to the A's? They cancel. Okay, and what that means is it doesn't matter how much stuff you start with. After the half-life, you'll only have half of it. If you start with 1 billion grams, you'll only have half a billion grams. If you start with 1 gram, you'll only have half a gram. Doesn't matter. Okay, Now, the goal here is to solve for k in terms of lambda. So how do we do that when k is stuck up inside this exponent? Yeah, don't need to use calculus anymore. What about just a log, right? Well, before we were discussing this before you decided to join us for class this morning, that I should do like in soccer and have like yellow card and red card penalties. And like if you get a red card penalty, you lose a standard you've already passed. Huh? Hey, it'd keep you guys on your toes though. You wouldn't come to class? Oh, yeah, okay. I don't know. Somehow I think he'd be amenable to that idea, right? Okay, so take log of both sides, and so k lambda equals the natural log of a half. The natural log of a half you could also write as the natural log of 2 negative. Okay, why is that true? Because how else can you write 1/2? Okay, and then you've got an exponent inside a log, so what happens to that? Pops out front as a constant. Okay, so if we wanted to solve for k in terms of lambda or lambda in terms of k, we just have to divide by the one we don't want. So lambda is the negative natural log of 2 divided by k, or k is the negative natural log of 2 divided by lambda. Okay, so that's how you relate half-life to this decay constant k. All right, so let's take as an example carbon-14. What did we say the half-life of it was, roughly? Yeah, let's just say it's roughly 5,000 years. So what is this number? Yeah, well, let's just look it up. Yeah, 5,730. Let's just go with 5,730. Okay, that's good enough for, huh? Well, I'm about to just pop it into a computer, so. All right, so negative log of 2 divided by, what did we say, 5,730. And then I want this, a numeric approximation of it, say to 10 decimal places, it's that, right? So negative 0.000, right? That's a pretty small number, okay? And in fact, let's even plot this. If we plot, so if this is our k, right, what we're going to plot is, well, let's just say I start with 1 unit of material. Okay, if I plot this over a year, okay, and since the half-life is in years, that means that we need to use years as our time scale, right? So if I start with 1 unit of carbon-14, how much of it remains after 1 year? Almost all of it, right? You know, 99.99% of it is still left, right? Because it is decaying, but just not very quickly. And so what should I see if I go out? Well, let's go out 10,000 years, right? Well, where do we hit 1/2? 5,730, right? Which, okay, we can't necessarily read that exactly off the graph, but we know that that's where it has to be precisely because that's what half-life meant, right? And so if I waited around, 11,400 years, how much of it should I expect to remain? Not a lot, but exactly how much? 1/4 of it. Okay, why is it 1/4? It's half of a half, exactly, right? So if I go out, let's say 12,000, right? And let me also just throw on here 2 other things to make this a little easier to see. I'll throw on some constants. Oh, that's not what I meant to do. I meant to put the curly brace here and there. Okay, so what's the orange curve? A half, okay. And how long did it take before we hit half? 5,730 years, the half-life, okay. And then how long does it take to go from 1/2 of the amount to 1/4 of the amount? Another 5,730 years. Okay, so this is one of the maybe easy mistakes that people make is you say, okay, if it takes 5,730 years for half of it to decay, then how much is there after twice that period? What's the trap answer? Huh? None. Right? Well, if half goes this time, then a half will go that time, but it's a half of what remains, not what you started with. Huh? I guess, right? I mean, the universe is an interesting place, right? Has to keep us on our toes. I don't know, I mean, this is why Dr. Brown says physics is the easiest major on campus. Huh? No, how could it not be true? I mean, you live in the natural universe every day, and all you're going to do is just study the natural universe in physics and learn to describe it. How hard could that be? I mean, he's obviously being extremely sarcastic, but yeah. Well, I mean, all models are bad. Some models are useful, right? So, okay, anyway. So, right, so radioactive stuff is going to decay like this, but obviously doing this for uranium, right, the time scale is significantly longer, right? The carbon stuff is nice because, right, things, when they die, they start with the ratio, sort of the usual amount, right? Because living things are going to absorb and get rid of carbon through, you know, respiration and eating and things of that sort, right? The ratio of carbon-12 to carbon-14 in living tissue stays roughly constant. But the instant you die, the material or the organism dies, it's no longer respiring, and so it's no longer, that ratio gets locked at death, and that's what we're measuring, right? In trees or bones or, you know, wooden axes or, you know, things of that sort. Okay, and so 500 or 5,000 years, right, perfectly good for doing anthropological or archaeological stuff, but it's not going to work if you want to study dinosaurs. Sorry. Okay. Okay, so notice, by the way, that this constant, right, if the constant k is negative, it's decay. If it's positive, what is it? Growth instead, okay? And so we only use half-life when we're talking about radioactive substances. That's just the word. But what would be sort of the equivalent thing that we might want to talk about with growth? Not half, but rather, how long does it take to double? Okay, so if I start with 1,000 bacterial cells in a Petri dish and I incubate them, then how long is it going to take before there's 2,000 cells? Well, it depends on a lot of things, but it's going to depend on, well, what's the temperature and what kind of cells and what's in the Petri dish, like what kind of agar have I put in there and so on, right? But there's going to be some number associated with a particular bacteria, a particular temperature, et cetera, okay? And now this model, by the way, is not particularly, it's only reasonable if you have, like, well, let's see how to put this. Is this model reasonable if you have one bacterial cell? No. If you have 1 million bacterial cells, is it reasonable? Yeah, okay. This mathematical model, because if you have 1 bacterial cell, you have to wait around some amount of time before it's 2. But is it ever 1.2 bacterial cells? No, that doesn't make sense, right? It's either 1 or it's 2. Right, so this is in some sense the way the model doesn't perfectly reflect reality, but if you have a large number of cells or a large number of atoms of something, then this is going to basically be close enough. Okay? All right, so does that kind of make sense? Yeah? All right, so let me, I know I kind of talked a lot about stuff that's not on the sheet, but yeah. So why don't you guys work out a couple of these problems, like the first couple of pages, and then maybe we'll start and talk about it yeah, on Monday. The other thing I wanted to maybe talk about just a little bit, because it's interesting, is one other instance of growth or decay, which is, you know, if I had my cup of hot coffee here, what's going to happen if I wait around an hour? It's going to be colder. But can we describe mathematically how that happens? And could I guess what the temperature would be after 2 hours if I knew the temperature after an hour? Well, I could, yes. I could just measure the temperature, right? But why do that when we could do math? Or, yes. Huh? What?
Like, even if you drink it, it would still have a temperature inside your stomach.
Well, it would, but it would be then. It would be, yeah. It would equilibrate to body temperature rather than the ambient air temperature, right? Well, we can model that too. Yeah. And I would much rather model that than have to shove something into my stomach for us to measure the temperature.
Cool. I guess that's what we're doing on Monday.
Yeah. All right, so anyway, I will see you guys on Monday. I will also have your reassessment to Paloozas and have fantastic